So welcome to part 2 video. So this video I am trying to derive the bending equation. So this is a previous KTU problem I have discussed in the last video. So I have seen we have already discussed what is the assumptions of bending and what do you mean by pure bending. Now what we will do, we will derive the classic bending equation. We will do this in two parts. This is the first part of the derivation. There is another part also. So without wasting time, we will just quickly start this. Okay. So assume there is a beam. Okay, so assume that I am actually putting a small patch of color in the beam. Small patch here. Okay, so let's say this is a simply supported beam. Now there are some loads acting on this. Because of the loads, what happened? This is bending. Okay, now this beam will bend. So let's say I am exaggerating the bending curvature and all. This will not look like this. The bending actually, and in practice, it will be very, very, very small. Okay. So let's say this is bending because of the loads. Okay. Now what will happen to this shape? Okay, this shaded portion may look something like this. Okay, so let's say this is a very, very small strip that I have taken. Very, very small strip. So this will look like this. So basically what is happening is, first thing that you have to observe is whatever portion in the top has shrunken, this length has reduced, and whatever portion in the bottom has increased. Okay, so there is a reduction in length, there is an increase in length. So I will isolate this portion here so that we can have a better idea. So original length was dx. Okay, now it is increased or reduced. Now we can say top it has reduced, bottom it has increased. So there will be some portion in between whose length has remained unchanged. Okay, so this is what is known as neutral axis. Okay, so you can say if let's say this is 10 mm, so we can understand this with numbers. I'm just assuming this is 10 mm. So this became something around let's say 5 mm, and this become something around let's say 15 mm. Okay, this is vastly exaggerated number. Now this is linearly changing, so that is an assumption. So that means in somewhere in between there will be another 10 mm. Okay, so basically there is a strip in center or somewhere which has not changed its length. That strip is what is known as the neutral axis. Okay, so I hope this is clear. So this is a very, very important part of our assumption. Now what happens? What I'll do, I'll just take this. With this actually we can continue our derivation. Now what will happen? So this neutral axis I'll assume to be a part of a bigger circle. So let me try to draw a circle here. So this circle has a radius . Okay. Now what is the idea? So this neutral axis, about the neutral axis I have drawn circle. So this circle has a radius r. Okay, so I hope this is clear. Now if circle is so big, so there is a small change in so this circle will be very, very big circle. This is a radius of curvature. Now the idea of this is very simple. Now if the neutral axis, this line, if I draw to look like this. Now if I draw the cross section of the beam, so let's say some random cross section it has. I don't know, it's not rectangular, it's some pyramid shape. So there is a centroid here. This neutral axis will be passing through the centroid. Now this is for materials which is obeying Hooke's law. Okay, so this basically the line joining the centroid will be the neutral axis, right? Now after bending, it will bend like this. It's bend like this. So it's a curve. This is a curve. It can be a parabolic curve. It's a cubic parabolic curve. It depends upon what is the loading, what is the boundary condition, all those things. Okay, but mathematically speaking, if you have any curve, if you take a very small portion of the curve, if you have any small portion of the curve, that small portion actually we can draw a circle. Okay, we can actually find a circle at that curve. So that small portion of the curve we can assume to be a part of some circle at some point. So it's a very, very small point. Any point on the curve you can take, and you can assume that small length to be a part of a circle. Okay, so this circle's radius is what is known as the radius of curvature of the curve at that point. Okay, so this is nothing but the radius of curvature. So I have taken a very, very small element in the beam. So neutral axis, it's a neutral axis. So this small portion of the curve I have taken. So this small portion of the curve can have a radius. So basically this small portion of the curve I can assume to be a part of a circle. And that circle has a radius. That radius is what is known as radius of curvature of this curve at this point. So dx is nothing but a point. It's very small. Okay, so this is the radius of curvature. Okay, now since I got the radius of curvature, what I can do is I can extend this. So it doesn't make sense. The drawing is not coming properly. So basically, we can assume that this is putting an angle theta at the center. So I'll draw it more properly now. Let me see. Give me a moment. So this is the original beam. So I'm sorry. So this shape should have been something like this, small part. So I have decreased this more than. So you assume that this both are the same shape. Okay, this both are one and the same shape. Now you can see here. So we can assume this small angle to be some theta or d theta. So let's say it's theta. This is r. Now from the centroid, what we will do? You will put points. Okay, so let's say from here, I'll take a small element which is at y distance from the centroid. So this distance is y. I am taking a small strip. Okay, so this small strip, original strip, I will draw here also. I'll draw here also. Okay, so these two are one and the same shape. Now give some names here, so it will be easy for us. So let's say I will call this as O dash, neutral axis. This is O dash. This is also O dash. Okay, and this I'll call AB. Sorry. This I'll call AB. This again is AB, new AB, so I'll call this A dash B dash. This is A dash B dash. Okay, now we know that O dash length is nothing but dx, is nothing but r into theta. Okay, r into theta, where theta is in radians, so r into theta is this chord length. Okay, now A dash B dash length, A dash B dash, not AB length, A dash B dash length or arc length is nothing but r plus y into theta. So this is r plus y into theta is this. So all these are basically part of the concentric circles. This is the center of the circles. So all these strips are part of concentric circles. So r plus y into theta is the arc length here. Okay, so A dash B dash is the final length of this small piece. The original length of the small piece was dx. Okay, so that means change in length. Change in length of AB when it changed to A dash B dash is, that I will call as delta L, is nothing but the length of arc A dash B dash minus length of line AB. Correct? So arc A dash B dash length is nothing but r plus y into theta. A dash AB, the length of this line is nothing but dx. Okay, but here we know dx is nothing but r theta. So I'll substitute this r plus y into theta minus r theta. So change in length is nothing but r theta plus y theta minus r theta. So this gives me y theta. So y theta is change in length. Okay, so once you find change in length, I can find the strain. So what will be the strain? So strain will be strain of AB will be change in length upon original length. Okay, now what is change in length? Y theta. What is original length? Original length is dx. So this is same as y theta upon dx is nothing but r theta equal to y by r. So this is what? Strain. So strain equal to y by r. Now Hooke's law. By Hooke's law, we know that Hooke's law tell me that stress upon strain equal to Young's modulus. Okay, so that means strain equal to stress upon Young's modulus. So I'll substitute it back here. So stress upon Young's modulus is equal to y by r. So I'll rearrange this term, gives me sigma upon y equal to E by R. So this is the first part of the derivation. This gives a relation between stress at any point y distance from the nodal axis in relation to Young's modulus and radius of curvature at that point. Okay, so basically what we have found, if you have a beam, if you want to find stress at any point on the beam, find the distance of the point from the nodal axis, that is y. Okay, find the radius of the curvature of the nodal axis at that point, that will be r. E will be the Young's modulus. E will be the Young's modulus of the material. Substitute all those values. Substitute the value of y, substitute the value of E, substitute the value of r, you get sigma. Now how do you find r? How do you find sigma? How do you find r? It's a problem. So we will see how we can find r and all on a later class. But this is the first part, first relation. This relation gives me the relation between stress at any distance y from nodal axis, bending stress at any distance y from the nodal axis to the radius of curvature and E. Okay. So this is the first part of the relation. We will do the second part in the next video. Right. Now also you have to observe one thing. How is the strain varying? How is the strain varying? Okay, there is zero strain at this location. Okay, so I'll just take this piece. So strain was given by y by r. Okay, so at a given section, at any given section, the r is constant at that section. For that section, this r is constant. Okay, for different sections, r will be different, but for a given section, r will be constant. So that means as y increases, strain also increases. So this is y. So as the y increases, strain also increases. Okay. Now we can assume one direction to be positive, other direction to be negative. So basically, where it is increasing the length, that will be positive strain. Where the length is reducing, that will be a compressive strain. Okay, but it is linearly depending upon y. So I can draw the strain distribution like this. This is the strain distribution. So this is the nodal axis, no strain. Nodal axis, no strain. This is a positive strain. This is a negative strain. Okay, but this strain, the value of strain is linear. It depends upon the distance of the point from the nodal axis. As we go away from the nodal axis, the strain will increase. As we go inside here, it is more compressive strain. As we go outside, we will get more tensile strain. Okay, so that means where strain is negative, there will be compressive stress. Where strain is positive, there will be compressive stress, tensile stress. Okay, so this is one thing that you have to understand from this. So we have done the first derivation. I hope it is clear how it has come and what is the physical meaning of all these things. Okay, so we'll complete this in the next video. Thank you.